This marathon of forces is almost over. Last question: Why do we quit? Why do we care? Been doing a lot of lessons. Okay, well, we have that raindrop. How cool is it that we can use what we've applied in the first 6 weeks of a physics class to actually find out how fast a raindrop is going when it hits your head, right? That's now within all of your guys' power, and I'm going to prove it to you right now, okay? So here's the deal. I want to start by doing a little quick refresher as to what that speed is. It's called terminal velocity, right? And how do we get that terminal velocity? Well, remember that if I have a raindrop or any kind of object that's falling through the air, right, or falling through any fluid, right, including a liquid, all right, I have a weight, right? And then as that weight accelerates that object, okay, like a raindrop, then I have a drag force being built up, okay? And when that drag force equals the weight, there's no more acceleration, and I've reached my terminal velocity, right? But that drag force itself is equal to 1/2 times the coefficient of drag times the density of the fluid that you're moving through times the cross-sectional area of a raindrop times v squared, right? And that's going to equal to m times g. All right? Does that make sense? Now, in this problem, I'm assuming that a typical raindrop has a radius of 1.5 millimeters, okay? And it's falling from a cloud that's at a height of 1,200 meters from the ground. Do you need that? No, it's a red herring, okay? I'm telling you that the drag coefficient, and this was my promise to you that I would give you all these values, right? The drag coefficient is 0.6 for this relationship between raindrop and air, right? And I'm assuming that this raindrop here is spherical, which means that its cross-sectional area will be pi r squared, right? And again, r is 1.5 millimeters, which is 0.0015 meters, right? And if this is spherical, then the volume of it, okay, the volume of this guy is 4/3 pi r cubed, right? And you're going to see that that's actually important, okay? What else do you need to know here? You need to know the density of air, right? This rho, so I'm going to do this density of air, and that is 1.2 kilograms per meters cubed. That's kind of crazy. What does that really mean? That means that if I have a cube, like a little box of air, right, and I lift that up, that's 2.2 pounds, right? Not just whatever's contained, not like the glass that's holding that air, but just the air itself. That's a little over 2.2 kilograms in that 1 meter cubed, right? Air is not weightless. And then lastly, we have the density of water, which we're going to actually need for, you're going to see why in a second. But the density of water is, you chemistry buffs probably know, 1,000 kilograms per meter cubed, okay? All right, now, we want to find the terminal velocity of this raindrop. In other words, what is the max speed that it gets to, which is the same speed that, the raindrop's eventually going to like collide with our little head, right? All right, so I'm putting a little VT there for terminal velocity, right? And if I solve for V, we get that V is equal to the square root of 2 times the mass times gravity, right, divided by the coefficient of drag times the density of air times the area. Okay, now, there's a couple things you may look at this equation and be like, man, I don't actually know that, okay? Now, one of those things is going to be the mass, right? What is the mass? I don't have it in this problem, right? You may be all like upset about it, okay? You don't have to be that upset because I gave you the density of water, right? And we know that density of anything is equal to the mass per volume, right? Okay, but in this case, we can find the mass and volume, right? That's just going to be rho times 4/3 pi r cubed. Okay, where this is, we're trying to find the mass of the raindrop, right? So that's the mass of water, so that's rho of water. Okay, when I plug in my little values here, right, my rho of water, which is 1,000, and my r here, which is 0.0015 millimeters, meters, and I put this in, then my mass of my raindrop that I get is 1.4 times 10 to the minus 5 kilograms. Okay, 1.4 times 10 to the minus 5 kilograms. Very, very small mass, which is what we'd expect. So that is the value that we're going to be putting in for here. Okay. G, as you guys know, is 9.8. C is 0.6. Rho of air is 1.2. Okay. And so now I'm getting somewhere, right? So my velocity, my terminal velocity, is just going to be the square root of 2, right, times my mass over here, which is 1.4 times 10 to the minus 5, times 9.8 meters per second squared, that's G, divided by my coefficient of drag, 0.6, times the density of air, which is 1.2. For the sake of space, I'm not going to put the units, times the area, but the cross-sectional area it's a sphere, so the cross-sectional area, as you see it coming down, that's just a circle, right? So that's pi r squared, and the r, again, is 0.0015 squared, okay? And so that means that the terminal velocity of this raindrop, the grand finale of this entire lesson, is simply going to be, I get 7.3 meters per second. Okay, 7.3 meters per second. That's not that fast, right? I mean, I couldn't run 7.3 meters per second, but as far as a raindrop goes, it's not something that's going to hurt, right? Maybe every once in a while there's one that kind of like stings a little bit, but it's not so bad, okay? And the reason why is because raindrops reach a terminal velocity because there's this thing called drag that balances out the weight acceleration that's pulling the raindrop down, okay? And you guys just solved this. This is well within your power, right? You basically just plugged and chugged into this terminal velocity equation, and you used some, basic chemistry and math to get there, okay? You found the mass of the raindrop using the density of water and the volume of a sphere, right? You found the cross-sectional area because you know that cross-sectional area of a sphere is just a circle, right? And the rest of this stuff is, anything you could look up online, right? So you guys are at a position right now where if you were at lunch with somebody and they're like, man, I really wonder how fast a raindrop goes, you could pull out your little napkin and solve this problem for them and amaze them, okay? And I'm proud of you for that. If you guys could go to the last slide, it says, hey, wait, where can I practice this stuff? I'm going to refer you again to the People's Physics book, and I have a chapter there on Newton's laws. I think this is a great book with problems that are at a good level to practice for exams. And so I hope that's useful. And man, this is an intense week. Thanks for being there with me.